la verdad es que es un placer presentaros a Manuel Rodríguez. Yo lo acabo de conocer hoy mismo físicamente, pero ya habíamos tenido alguna interacción previa. Manuel es gallego de origen, de Pontevedra. Igual nos cuenta, ahora se acaba de comprar una casa aquí para al menos pasar los veranos y ojalá sean más que los veranos. Está en el Planck, estudió ingeniería eléctrica en la Carlos III de Madrid, después hizo el máster y el doctorado en Stanford. Y bueno, yo creo que se podría resumir su trayectoria brillante a nivel científico diciendo que tuvo una RC, una starting y ahora tiene una consolidator. Hay muy pocas personas realmente que enganchen dos, muy pocas. De hecho, hay muy pocas personas que tengan una RC en cualquiera de los tres tipos que existen, pero ya que hayan encadenado dos, son muchísimas menos y eso, bueno, pues yo creo que resume una trayectoria realmente de enorme éxito. Pero además el tema en el que trabaja es un tema que nos interesa mucho en el centro, aprendizaje automático, y además un aprendizaje automático pensado, aquí sí, muchas veces se hace ese discurso de IA para el ser humano, centrado en el ser humano, en fin, él trabaja en esos temas precisamente, que sabéis que también son una línea importante dentro de las líneas de investigación del centro. Bueno, en fin, su currículum es realmente fantástico, con premios, reconocimientos de hecho tiene un mejor Best Paper Award en Eurix, que es uno de los congresos, si no el que más importante en este ámbito. Y bueno, pues es un placer, Manuel. La verdad es que estamos contentos de tenerte aquí, esperamos que sea una de muchas veces. Hoy no es el mejor día desde el punto de vista de asistencia masiva, pero bueno, seguro que sacaremos muchas cosas de interés y el tiempo es tuyo, cuando quieras.
Gracias por la introducción y gracias por venir. A partir de ahora voy a hablar en inglés porque si intento dar la presentación en castellano no va a ir bien. Y además las transparencias y todo las tengo en inglés, pero si queréis preguntar algo en castellano me preguntáis y os respondo en castellano. ¿Vale? Y yo, también si hay alguien que no hable ahí si castellano perfectamente, pues a lo mejor. Today I'm pretty excited to tell you a little bit about a line of work. Basically, that is about how to use machine learning for decision making, and to do it in a way that is kind of providing some kind of reliability guarantees. You know that when you use ML, you take some decisions, and you can make sure that the machine learning system is not kind of misleading you. So it's as Senen was kind of pointing out, there is also kind of this promise of using machine learning in many domains in which important decisions are being taken. And the idea is that these machine learning systems, they are going to provide some kind of decision support in these domains. And you can think in things like health, where there is a doctor that maybe wants to use a machine learning system to help diagnosing a patient, or things like even to do science discovery. I guess maybe some of you are aware of, I don't know, DeepMind saying, oh, they managed to use machine learning to discover some new theorems or stuff like that in mathematics, or also for education that you would say, I saw that you have a very fancy thing downstairs where you, for example, try to actually use some kind of technology, computing technology to improve education. In this case, put a decision support system based on machine learning to kind of help a teacher to deliver a lecture that is somehow more effective. So in this domain, I guess something that you would expect is that, when you work together with some machine learning system, you take better decisions. The doctor is somehow taking better decisions with ML than without. But traditionally, if you look at the machine learning research or artificial intelligence, many times the goal was not that, but was more you have this AI system that would work autonomously, kind of would replace a human. So they are not designed to work together with them, but they are designed to kind of work automatically. But in some of these domains, probably it's not even, maybe you wouldn't feel comfortable to go to the doctor and having a machine that somehow tells you what you have and what you have to do, but you don't interact with a human. I hope we don't arrive to kind of that future soon. So you would like that somehow the doctor is using these systems, but to work together. And as a consequence of this, that they are not designed to work together, you have something that happens, and there is empirical evidence, even many papers shown that this may happen. No, if you think that you have some measure of performance for some task, let's leave it at that, not like something super concrete, no, but that you would say, oh, there is a person alone would have some kind of performance in this task. Okay? If you would deploy the machine learning algorithm and you would say, oh, let's the machine learning algorithm to solve this task automatically, and would do maybe better than the actual human. But when you try to design a system that you would tell the doctor, here is the system, you can use it whenever you want to take better decisions, in the end, the doctor or the decision maker plus the machine learning system is somehow worse than the machine learning system alone. No, and there are in many domains that this happens, and this somehow can be a justification to say, well, we should just, I guess there are many high-profile figures even in machine learning that would say, oh, radiologists should be substituted by machine learning algorithms because they are better, no, because they kind of claim, oh, if you put the human in the loop, makes it worse. There is also some other situation that happens sometimes that you would say, oh, it's a task in this, in which humans they are still better than a machine learning algorithm, no? And you would say, oh, in this case, it's even more difficult that if you give access to the human to the machine learning algorithm and they work together, actually you decrease the performance of the human, no? Because it may happen that the machine learning system is actually kind of misleading the human in some cases, no? And a bit idea, no, is that the motivation of our research in this particular context would be to try to avoid these kind of situations. Not that you would say when you give some AI, ML, machine learning support system to a decision maker, it improves things. Okay, and it improves things reliably, not like sometimes, but by design. So in this particular talk, I will focus in some task, no, that is. For those of you, I guess, maybe they work in machine learning, if you go to any machine learning class, is one of the first tasks that you would talk about is what is called this kind of classification task. Okay? And to give you a bit more idea of, with an example, what we will focus on will be in this kind of task, whether you would say there is a data sample. In this case, I just showed you an image. No? You can think here, oh, it's an image of some land, some X-ray. And based on this sample, no, there is some kind of features that is just a digital representation of the image. And you would say there is a machine learning algorithm that based on this image in this example would tell you, oh, there are certain kind of diseases that the patient of this image may have, and is trying to predict, oh, this person has a pneumothorax. Okay? So this is what is called the label. No? That you would say in a classification task, there are multiple classes, in this case diseases. You would like the machine learning algorithm based on the data to actually tell, oh, to predict what is the disease, or in this case, to kind of infer what is the disease. And in this setting, in decision support now with ML, would be that afterwards you have a doctor that receives this prediction by the machine learning algorithm, and together with the image and potentially other information. I mean, typically doctors, they would have access to the patient, no? And they could ask the patient something else that is not even used by the machine learning algorithm. Okay? And based on that, somehow the doctor in this example is diagnosing something. And in this case, turns out that I mean, I'm not an expert, but I did check this image. Actually, the patient has an emphysema, doesn't have this pneumothorax. No? And in this case, the doctor actually realized, oh, the machine learning algorithm was wrong, no? But and diagnosed correctly. But for the remaining of the talk, no, I'm not sure. At least I'm not an expert at all in medical images, and I believe I would be surprised many of you are. So to keep it simple, we will work with kind of images that they are easier to recognize what is in the image. Okay, like something in this case is a track that is kind of pixelized, but something like that. But the kind of idea is the same. No, the machine learning algorithm may make some mistakes, and the person in this case, I don't know, detector of automobiles or whatever, would recognize, oh, what is there is a truck. It's not a pickup. So here, no, the way that I introduce this this example and this setting, no, is in a way that no, if the machine learning system is not perfect, meaning that never fails in what predicts, you would expect this kind of system that the expert needs to understand when to trust the system or when to actually go with whatever is the guessing of the human. No? And yeah, this follows from the fact that there may be some data, some samples in which the machine learning system is very good and never makes mistakes. But there may be other type of data that the machine learning system may actually make mistakes. And you would expect that if the person is able to recognize when to use the system and when to ignore the system, then the person would be better off, but otherwise may happen that actually it's better not to use the system if the expert starts to be misled by the system whenever it makes mistakes. And yeah, I mean, I guess I'm not the first one that was highlighting this thing that, oh, when you put this kind of what is called in ML classifiers, this thing that they predict some kind of label, that would have to happen that the person using them has to develop some kind of sense of when to trust them. No? And there are even entire fields of research that some of the motivation within machine learning is that. One of them, I believe you will be familiar with some of the things I will talk about, that, for example, no, there is this idea to say, oh, that is also a buzzword, that you would say there is explainable AI, no, explainable machine learning. That you would say, oh, it's not that you are going to provide only the prediction, but the system is going to tell some kind of explanation. No, that they would say, well, I predicted pickup because, you know, here there is this shape or there is any kind of pattern in the image that somehow would help us understand whether the system is making a mistake or not. Okay? If it would say, oh, I predict track because, you know, the background is green, then you would say, oh, that doesn't seem like a plausible justification of this prediction. So there is a huge amount of work that focuses on that, on kind of designing explanations. There is some other line of work in machine learning that you would say is, you could tell is kind of about uncertainty quantification, that I guess in the case of language models actually has become quite popular to say, oh, they should be able to tell you how confident they are. Not that to say, oh, my prediction is that it's a pickup, and I think I'm 30% sure, whatever that means. No? And the idea is that in that way, you could recognize, oh, if the system is very uncertain about the prediction, maybe I should be skeptical, no? Because it may happen that it actually is wrong. And there are other things that you would say they are more global, no? That I guess when you go to a plane, probably if you see, oh, that they tell you, you know, the probability that the plane crashes is super, super low, no? That these kind of things that they would tell you also the prediction is correct, in this case would be quite low, but like 80% of the times the prediction is correct or something like that. So all these things is like the motivation for them to, for the people to do this kind of research is to say in the context of decision making would be, oh, this would help the decision maker to develop some kind of sense of when to trust the predictions or when to ignore them. But a fair question to ask, no? I mean, if you go to, I don't know, Google Scholar and you try to find things about explanations, you will find thousands of papers, like tons, no? But in the case of this decision support system, whether there is a human that is kind of on the loop and you want to say whether they are effective for this scenario of helping a human use this system, turns out that there are empirical studies showing, oh, much of that information is kind of not always very helpful. Even if I tell you the system is, the system tells you is 70% certain, it's unclear what to do with that information. No? Is that where do you put the threshold? Where do you decide to actually trust it or not? All that is kind of not trivial. No, you would have to learn how to use all this additional metadata or information to kind of decide when to trust the system. And turns out that is pretty difficult. And there are many studies that show, oh, the AI alone is always better. So the human should be removed somehow, no? But the idea is, okay, if to change the paradigm to say, oh, you want to design a system that even if it is very accurate, if the human has additional information, you would expect the human maybe to help, no? Especially in this setting where the human can, interview another individual to gather additional information that by the moment a machine cannot directly do. So our idea now was like, okay, since it's not clear how to make sure that experts in this case develop this kind of sense of when to trust the system. No, so as a motivation, we wanted to say, can we design a system where does it depend on that to help a decision maker? They don't have to do some kind of guessing a mental model of the system for not being misled by the system. And that was kind of the motivation. And here is one simple idea. So in this context of classification, no, you have the issue, no, that I was mentioning at the beginning, that there may be some examples that they are very easy. So the system never fails. You know, the first thing that you see here, I guess, despite all this pixelization, you would, all of you, I think, you would recognize this is a track. Okay, but if you go to the last image that is here, there is an animal there, but don't tell me which one was the animal. I don't recall, but it's not a goat. Okay, but it would be very difficult. But in this case, no, the system, whatever is the image, will try to make a prediction. And that happens for neural networks, anything fancy. You ask, I don't know, you put the, here in GPT, whatever, you put the image and would have a guessing, no? And would try to explain it. And doesn't matter whether it's a mistake or it's not a mistake, we try to do it. So independently of how difficult the example is, it's trying to always solve the task. Okay? So here our idea was the following, to say, we are not gonna ask the system to always solve the task, but rather to say, if the example is very simple, okay, we'll solve the task in the sense that we'll make one prediction. Okay? But if it turns out the image is very difficult, we'll actually give a set of predictions and to say, okay, large enough to make sure that among the set of predictions that is giving you, thinks the answer is there. Okay? So in the extreme case, if it turns out it's an example that the system is super uncertain about, you would say, oh, would give us a set all possible options for this domain. Okay? So in that way, we are kind of simplifying the task. If the task is very simple, you just is the same as a traditional system. If the task is very difficult, you provide this kind of prediction set of predictions that is very large. Okay? And now if we come back now to this kind of motivation example of how this decision support system works, in this case would be the same now that you have some data examples, some features, and here the decision support system is providing a set of predictions. Okay? And as we said, this is going to be dynamic, sometimes very big, sometimes very small, depends on the difficulty of the image of the data. Okay? And here, one of the key points is that the human expert, we ask the human expert to kind of pick from this set of options. So in a way, we are kind of restricting the agency of the person. Okay? We don't ask the person to say, oh, you have to choose whether you trust the set. If the set is very large, we ask you to pick from this set because somehow within the system, otherwise it's going to fail. If it is very small, may happen we reduce the agency, but we are pretty certain that the answer is correct. Okay? And in the example before that I was saying, oh, the system was giving us a solution track, and pickup, and the expert was recognizing was a track. In this case, since there was some kind of uncertainty, the set will be larger, so we would ask the person to pick from the set, but the true answer is in the set. So in this case, no, it's like we don't ask the human to understand when to trust the system or not, but rather we modulate this kind of agency that we give to the expert. If the system is super uncertain, it's as if the expert would choose alone, because the set will be very large. If the system is very certain, the set would be quite small, so we would prevent an expert from making a mistake. No, because we'd say, oh, if the expert was kind of going to pick the wrong thing that is outside the set, doesn't pick it anymore. Okay, but one question now here is to say, okay, if we are reducing the agency, and only to give you an idea, because sometimes when you hear this thing of, oh, we are going to reduce the agency of the expert, oops. Yeah, I'm not sure if it was the opening of the door. Oh, should I just disconnect and connect? No, yeah. Yeah, nada. Ahora sí que está. Si no lo tocamos. So to give you a sense, not when we say, oh, that otherwise, I mean, no worries.
But for sure, it's
or,
problem with the...
I mean, durante 20 minutos no se movió.
No. ¿Sabes lo que vamos a hacer?
Yeah.
¿Qué pasó?
No, que se... pero yo creo que está
es un
bien.
problema de conector, pero cruzándolo un poquito quizás. A ver, pues sí.
Yeah.
Maybe you have to stay there.
Go out.
So, I mean, when you hear this thing of, oh, reducing the agency, you would say, oh, that is not really realistic, how it's going to happen, no? To give you an idea, okay, when you go to a plane, no, it's like, okay, there are some automated things that prevent the pilot, for example, to take some actions in the middle of the flight or something like that, no? So there are commercial systems where you would say, oh, as a way of helping whatever is the expert, they are reducing the agency. So it's what we are saying here, but at the same time, we want to make sure, oh, if we reduce the agency, we have to make sure these sets that I was talking about, they always contain or very reliably contain the true answer. No? And this is something that, I would like to give you a bit more technical details about how this is done, that I'm not sure you will ever, I mean, only to make it that it's a little interactive. How many of you heard about the word conformal prediction? No, okay. Then I will do kind of a primer on what does it mean, this conformal prediction thing. So, this conformal prediction is something that is some statistical technique, no? That is to construct this kind of, we will see what it means, trustworthy prediction sets, no? By trustworthy prediction sets is that to conformal prediction, you could say, oh, I want a trustworthiness of 1 minus alpha, that you could say, this is 99%, or this is whatever, 99.999%, no? Some kind of what is called coverage. And then the way that we'll construct the sets will be such that guarantees that with this kind of probability will happen that the true answer is in the sets, not in expectation of all possible data that you may have. So if we say here, oh, that we want 1 minus alpha to be 3/4, would happen that in 3/4 of the samples, the actual sets contain the true answer.
But the site coverage probabilities
by the designer, by you. You could say, you can choose whatever you want here. You can say this is super high, or you could say, well, you know, I'm fine still if there are a few mistakes, meaning that the true answer is not in the set. No? And this is something that you decide. Okay? And this technique, no, why it became popular in machine learning, or relatively popular the last years, is because somehow you can start with your classifier that can be a neural network, can be whatever super complicated thing you want. You know, can be a model that you run it in a cluster or something like that. And given this model that is a huge thing, to conformal prediction would just take what is called, well, if you ever use a neural network, there are this concept of softmax that you would say, oh, it's the confidence that the neural network has in each of the possible labels. No, when you use a neural network, would tell you, oh, this is kind of the confidence of that the image is a car, is a truck, is a pickup, and usually in the standard setting, you take the one with the highest confidence, and that is the prediction of the neural network. No? And the one with the highest confidence in this case is pickup. That was a mistake, and would be pickup. No, in conformal prediction instead, uses a threshold that we will see how is it computed, and anything that lies above the threshold is actually, I mean, it's included in the set, in this prediction set. So in this case, if the threshold is Q alpha is here, no, there are two potential classes, two potential labels that label values are above. So the set that is why it contains track and pickup. But the key point now is to say this Q alpha would be a threshold that, depending on the coverage value, depending on this 1 minus alpha we want, will be lower or higher. No? And how is it done? So it's done the following, no? That you would say, you have some data that is this calibration data set that you would say some images that you know the true class. Okay? And for these images that you know the true class, what you do is to say, oh, you use your neural network in all these images that you know the true class, and you just compute what is the confidence of the neural network for that true label for all the images. And this kind of confidence, you can have this empirical distribution of confidence for all your samples in the calibration set. Meaning, will happen that for some easy samples, turns out that the confidence of the neural network is very high. But for some very hard samples, will happen that the confidence of the neural network is low. And that, is the true labels. No? So you can have this kind of empirical distribution. And now this Q alpha that I was setting, conformal prediction, what it realizes is that you just compute the quantile of based on this data that you have, so that you know that, okay, for 1 minus alpha of all these samples, the value of the softmax is higher. And for alpha of them is lower. Okay? So in a way, if you set the Q alpha to that value, you know that now when you are using your system, will be 1 minus alpha chances that if any softmax that is higher than Q alpha, you include it in the set, then with probability 1 minus alpha will happen that at least you include the true label. Okay? And the trick is that if you want your coverage to be higher and higher, you put a Q alpha that is lower and lower, but then you will see now what is the problem, no? That the sets are increasing. Meaning that, okay, if you want a coverage that is 0.99, you end up with a bigger set because you put your Q alpha lower. If you put it that you are able to, actually, you are willing to miss some of the true predictions, then the sets are smaller, but you actually miss some of them. Okay? So it doesn't come for free, no? It's not that you would say, when you were asking, I guess, oh, 1 minus alpha, you can pick it, so it's kind of magic. No? Then you would like always to be super high. But if you like it to be super high, means this is super low, so it means that you accept every label in the set. No? And here is one of the, I guess, the key idea that we realized was the following, no? That if you think on this, for all possible values of this alpha, no, you would say, oh, in this kind of area, will happen that, oh, the set always contains the true label, but doesn't help the human much, because anyways, they are so large that it's as if the human would be alone. In this other area, happens that, oh, the set is very small, but sometimes you mislead the human, because it's like, okay, you give this set that is super small, but the true answer is not there. So you are actually making the human to make a mistake. And the key idea would be to say there will be a sweet spot, whether you would say you choose an alpha value that is high enough not to make the human to make mistakes, but low enough so that, low enough, the alpha, the humans not to make mistakes, but high enough to simplify the task. Because if they are always super large, you are not simplifying anything. And in this kind of alpha star, would be the best value for this coverage, for this design of the sets, so that they improve the performance of both humans that they are obliged to pick from the set. Okay? But when I said this, one thing that is, I guess, key is to say, with some caveats, but if you would choose alpha 0, would be as if the human would be alone, because the sets would be the entire set of labels. If you choose alpha 1, it's as if the sets are like the original classifier. They are always singletons. They are always one item, but you may, so these two solutions, the 0 and the 1, are basically, here is the human alone, and here is the machine alone. So if you are optimizing for alpha, you are sure that you are better than any of these two extremes. Because if it turns out the alpha 0 is the best you can do, that is to leave the human alone, that would be the best alpha. If it turns out in this case, the machine is the best, so would be chosen 1. So in that way, we, in this kind of setting, whether you are trying to help a person to predict something, would be in a way that by design will be better than the person alone or the fancy neural network alone. Okay? And after I will show you something with actual humans and an actual system, but to give you a sense, no, like what we also did is to say for many different classifiers with different kind of accuracy here, we kind of simulate a human with different kind of accuracies alone. And because of this property that we are saying, we choose the alpha that you know is the best. So we can always make sure that if the human alone is this accuracy, the human plus a system that even is, for example, here is lower performance than the human, this is 0.7, this is 0.3, it still helps a little. And how is that possible? Because for this 0.3, you will end up choosing some sets that they are larger. Okay? And in the other example now here, you would say a human that is 0.3 happens that a classifier is also actually helping the human to improve always by design. Because of this trick of saying you ask the human to choose from the sets and you design the sets in a way that you are guaranteeing is better than the human alone or the machine alone. But this is just like a proof of concept to kind of tell you, oh, this thing, you are all going to be always better than the human or than the classifier alone by using this kind of paradigm. And after we will see with actual humans that actually improve. Okay? But also to give you a bit of some technical details, no? I was saying, oh, this is for the best alpha that you can find, no? This alpha star, to say, oh, this is the best parameter. But how do you find it? No? How do you find it in a way that, these systems, if I claim they are deployed with humans, it's like, okay, are you going to try all possible alpha values with tons of humans using the system since kind of not scalable? So here we use something, no, that maybe just to, again, kind of know a bit if some of you heard about it. Did somebody of you heard about bandit algorithms? Okay, one person. Okay. Yeah, well, just as even here will be less details about what is this bandit thing, but a bit idea, no, of these bandit algorithms is that you would say you deploy your system, meaning that you have your classifier, and you want to decide the value of alpha, and what you do is over time, a person comes to use the system, you choose one value of alpha, and you keep changing these values over time as you get more people to use the system, but you are prioritizing the values that they seem more promising. Meaning that once you realize, oh, with this alpha value, people tend to make less mistakes, then you start to gather more data with this alpha value, but you still try a few others, and you are kind of exploring and what is called exploiting. That means, over time, you are kind of concentrated on the values that they seem to be the right values closer to this alpha star. And there is a huge literature in machine learning about designing these bandit algorithms in a way that is efficient, meaning that you need not so many attempts to actually end up with the best value, in this case, this alpha star. Okay? Because in this case, never mind. And among these algorithms, no, there are many flares, and it's an entire field of research. But what is somehow a little underwhelming, no, is that many of these algorithms would be something not realistic in terms of number of attempts. No, if you would say, oh, that they would need thousands of iterations, or something that you would say, oh, how is that realistic to start deploying a system, I don't know, for diagnosing patients, and that for a long time the whole thing doesn't really work, then you wouldn't use them, no? But in this case, we realized something that I guess relates to this consolidator grant, that is some insight that makes that this whole thing is much faster to find this alpha star. That I think intuitively is quite easy to understand and exploit something about human rationality, I would say. That you would say, okay, you have here your set, no? That this set was provided as a set by conformal prediction for some value of alpha. No? In this whole process, you choose the value of alpha, you get a set, and you see what happened to the human. And based on that, you may say, oh, this alpha value is good or bad or whatever. So, but when you do that, no, for this particular example, there may be other alpha values that would lead to a larger set or to the smaller set, but you don't know anything about those in principle. But now imagine, no, that for this example, turns out the human here that was able to actually find the true answer. No, that in this case the true answer was track. Okay? So intuitively you would say, oh, if this human, given this set that has 3 elements, was able to find the true answer. Now if here I would give the subset of this set, that is this track and pickup, still contains the true answer. But you would say, oh, but the task is even simpler because there are only 2 alternatives. If the human managed to find the true answer with the 3 alternatives, we kind of argue that would be able to find it with 2 alternatives that are a subset. No, because it's a simpler task. So in that way, you would say, oh, we are going to somehow try, and in practice works, to say, oh, despite we didn't really deploy this system that correspond to another value of alpha, we didn't deploy it. But we are going to infer counterfactually that the human would have still found an answer. And this helps us to get additional kind of data that to be able to tweak the value of the alpha thing. No? And on the other hand, is the other case that you would say, oh, what happens if the human actually didn't manage to find the answer here. You would say, well, if I take a superset that contains this thing, the task is even more difficult. So we would still claim, oh, the human, would still fail because was failing for a set of 3. Now for this set of 4 that is even more complicated to find it there, would infer that. So again, here we would have some kind of counterfactual prediction that you would say, oh, this would have happened. Okay? So when we are deploying this system and over time trying different values of alpha, we are counterfactually inferring what would have happened in other values of alpha using this insight. Okay? By doing that, we are getting kind of data for free. Okay? And what is more surprising, that maybe for you, maybe you understand what I'm talking about now, but for others, I mean, these algorithms, the way that you test what is efficient is this idea to say there is an optimal value of alpha that if you deploy the system for t times, you would say, oh, there will be a performance for the optimal alpha, and then will be a performance of the alphas that you are choosing over time using your algorithm, And the gap between these two things is what is always in this bandit literature is always about that, That you would say you would like that your way of deciding alpha values is such that converge very quickly to what would be the actual performance with the optimal alpha value. If this thing is small, then you would say, oh, the algorithm is better, is faster, because it's over time, and you would like that, oh, what is called regret is something that is sublinear on t, meaning that, okay, as you increase the number of times that you try your system, this whole thing reduces faster than linearly. And what we are able to show is that for some algorithm that is very classical, you have some kind of term here that depends on the size of your calibration set, this set that I was talking about at the beginning. And we managed that there is an exponential improvement on this set. So that instead of having this term m in the regret, you have a logarithm of m. So that is a big deal. It's like, okay, it's like in terms of order of 1,000 would be order of 3. And that makes it that it's much faster if we use this trick of these counterfactual predictions to find the value of alpha. Okay? And to kind of switch a bit gears, to say, oh, everything I said, especially the last part, maybe you think all these things seems very theoretical. You are kind of a bit separated from reality. But to come back a bit to something that seems more real, we wanted to say, after all these things that I was telling you about, that actually we try something with actual humans in a task that is kind of a bit of a toy task, but is still not so toyish. So we ran some experiment with almost like 3,000 people that we saw tons of these kind of natural images I showed you about. And a bit the idea now is that, we saw some image that is not completely obvious what is in the image. And we give the human some kind of option to say, these sets. And as you can see here that we have tons of predictions that we ask the humans and so on, is because we kind of brute force it. I mean, we ask for all possible prediction sets. We gather data for all possible prediction sets for all the images we have. So that in a way we can see the performance under any different value of alpha. Okay? And so in this setting that we call this strict implementation, we really ask the people to say, pick one thing from this set, and they cannot choose anything else from outside the set. But I guess some people that we talked to during the development of this work, they were always skeptical to say, no, I still believe that if you give a choice to the people to choose something from outside the set, will be better. And then we kind of, in this study, we actually gave the option in a parallel kind of the control group or to say, that you can choose from the set or you can choose other, and then you can choose anything you want. And a bit idea was to kind of, in this, what we call linear implementation, the people always have agency. They can always decide, I ignore the system. I choose other if I want to, and I predict whatever is outside the set. And if I trust that is inside here. But the way I'm talking about it seems that, works. And the point is that, we managed to show, this is different values of alpha. For the system, this is kind of the humans alone, like real humans. This that is here the performance of the, in this case, was a neural network that is very famous for image classification alone, no? And what is here in blue is this kind of a strict implementation that you reduce agency, I mean, what I was talking about all the time. And the orange is the part that is, you allow the people to have a choice. No, and when you allow the people to have a choice, the performance is actually worse than, and consistently, I mean, here is kind of the gap, in relative terms is quite large. So, and a bit idea, no, is that, in this particular case, with these kind of prediction sets, if you are lenient, you improve a little bit over what the machine would do alone. No, but the improvement is very little. But in relative terms, also if you are strict, I mean, you do what I was describing, then you are able to kind of improve, okay, 4% in relative terms. That is more of an improvement. No, but I'm not saying all the time is that, by reducing agency you will do better. But in this particular setting, it seems that, by not letting the people choose when to trust the set, but to this thing, you end up having like, better performance. And what I presented you today is the result of, I guess, 2 papers that were in ICML, that is not NeurIPS, that is kind of the other major machine learning conference. That they were, this is the part that we ran this counterfactual prediction idea and the decision and the kind of human subject study, and this was the original idea of using these prediction sets with conformal prediction. And this mainly was the lead author of both was Eleni, that is a PhD student in my group, but also Luke, that was an intern, and Astaran, that is another PhD student, were involved in the first paper. And this is everything I had today, and thanks a lot.
Gracias, Manuel. ¿Preguntas?
Sí.
I was actually wondering about the bandits. Why, well, I'm not an expert, so I'm just asking out of curiosity. Because when I saw the alpha optimization thing, the first thing that came to my mind was Bayesian optimization.
Is that I guess in the first paper we didn't use bandits. We use not still Bayesian, but I guess the part of the bandits is that this thing that I was talking about, the prediction sets, you don't have any prior. You don't use any prior for having the guarantee. And in bandits, the way at least we derive it and so on, you don't use any assumption either about the human. You don't assume that humans follow any, there is no Gaussianity, there is no assumption about the humans. You could also say, for each value of alpha, you try to infer a Gaussian process or whatever, and that is also possible. But in this case was, I guess it's also possible. But was the idea of, to do something that is kind of distribution free. That you don't assume anything, but it's actually possible, and probably the trick of the counterfactual predictions, you can use it still for a Bayesian kind of approach. You can still include those counterfactual predictions as data to compute the posterior. But, sí.
Bueno, entiendo que, claro, que lo que estás presentando, por ejemplo, si trabajas con imagen médica, pues tienes que hacer un sistema doc para calcular los alfas, por ejemplo, si vas a trabajar con imagen radiológica, presentas el uso, tendrías que trabajar siempre así, ¿no?
Sí, y es también, depende de decir, si una persona va a utilizar solo una persona al sistema, pues podrías encontrar el alfa que es mejor para esa persona, ¿no? En los experimentos teníamos como 3.000 personas, pues el alfa que encontramos es el alfa que es mejor para esas 3.000 personas en media. Pero también es porque si tienes una sola persona, también le tendrías que preguntar a esa persona, resuelve todo esto antes durante el diseño, y sería como más burden en la persona en sí. Pero sí, lo puedes hacer personalize, y también puede ser lo que dices tú, que si es para un dominio en particular, puede ser que la mejor alfa es una u otra, porque también depende un poco del clasificador y depende un poco de la persona que lo use. Pero todo eso es como que dependiendo del dominio tendrías que como hacer la optimización para ese dominio.
Los clasificadores con los que trabajáis te tienen que dar siempre lo que es la probabilidad de
no tiene que ser realmente probabilidad, puede ser como un score. Porque, por ejemplo, lo que usamos era uno de estos una neural network que ponemos el softmax, pero digamos que el softmax no es que sea una probabilidad calibrada ni nada así. Puede ser, pero puede ser cualquier cosa. Todo esto, lo de conformal prediction, es que tienes que tener como un score que para cada una de las clases tu clasificador te da un score. No tiene que ser probabilidad. Y basado en eso, tú tienes la empirical distribution de los scores de las clases que son las true classes y usas eso para tener el threshold. Pero el threshold puede ser sobre scores que sean, ¿sabes? Que sean cualquier cosa, la distancia, la frontera o cualquier cosa que no sea probabilidad en sí.
Entonces, digamos que el alfa al final no es una cobertura.
No,
Puede ser una aproximación a la cobertura.
No, el alfa es siempre una cobertura porque es en plan, basándote en esto, ¿no? Es algo así como dices, el Q alfa es como el quantile de tus scores, que tus scores pueden ser no probabilidades, pero después es simplemente usando, es como order statistics. Una vez que tienes esto, y esta garantía que digo que es lo de 1 menos alfa y tal, es como, no es en el límite, que es la cosa que es un poco rara de conformal prediction. No rara, pero también buena. Que, por ejemplo, si tú esto tienes, pues tu calibration set es de, pues no sé, 1000 datos, ¿no? 1000 imágenes. Pues entonces, algo que no explica aquí, es que esta garantía de 1 minus alfa sería como 1 minus alfa más menos 1 dividido de 1000. Que como el error de los finite samples es este 1 dividido de 1000. Pero eso es como que no es algo que digas, en el límite cuando el calibration set es infinito tienes 1 menos alfa, pero si no, no sabes nada. Sí que lo sabes, pero no puse ahí lo del error que tienes, que es muy pequeño.
Dos preguntas más. ¿Habéis valorado en qué medida esta aproximación aumenta la confianza del usuario en el sistema? Y dos, a ver si la recuerdo, pero se me fue.
No hicimos en plan de qualitative questions, de decirle a la gente si esto aumenta tu confianza o si no hicimos nada de eso. Porque en el sentido de hay como también research, ¿no? Que preguntan a la gente que hacer de estos self-assessment de su experiencia y muchas veces es que hay bastante divergencia entre lo que la gente piensa y lo que realmente cuantitativamente pasa. Y entonces en este caso tampoco teníamos para hacer esto, ¿no? De decir, que podríamos decirles, porque pensamos de hecho en esto, de preguntarles preguntas de, si el hecho de que aquí no pueden elegir de fuera y aquí, que preguntas de decir, tienes te da la impresión que el sistema te forzó a a cometer fallos que no cometerías y tal. Y eso no tenemos, pero lo que sí que tenemos es una cosa que es un poco, ¿por qué funciona que cuando restringes al final la gente es mejor que cuando no lo restringes? En este experimento en sí pasa, ¿no? Que cuando resulta que la solución no está en el conjunto, pasa que porque también tenemos datos de la gente para cada uno de los ejemplos como sola, con un set que es, ¿no? Y entonces sabemos que para los casos en que pasa que utilizando esto de los sets, la solución está fuera, la gente sola hubiese también cometido un fallo. Con lo cual no es que en sí, ¿sabes? El algoritmo les induce a cometer el fallo. El fallo lo hubiesen cometido igual. Entonces, en ese sentido, es como, por eso pasa que cuando le das a esto, si resulta que aquí no está, cuando le dan a other, no son capaces tampoco de encontrar la solución. Y en los casos que dirías que ayuda, ¿no? Que sería, bueno, esos son los casos que ayudaría, darle la opción. Con lo cual, en ese sentido, no les preguntamos, pero en la mayoría de los casos sería que la persona no es que hubiese encontrado la solución, pero no la encontró porque el sistema le restringió las opciones. Pero tenemos ahora otro proyecto que es un poco distinto, es también de restringir un poco agency, pero que ahí sí que planeamos preguntarles de su experiencia, pero es más como resolver tareas que son secuenciales, que es que no es así como esto, que es una sola imagen, pero es más una cosa bueno, es con un juego y tal, pero es una cosa que tienes que encontrar unas acciones a lo largo del tiempo que son óptimas y restringimos el tipo de acciones que pueden tomar. Entonces, en ese sentido, sí que les preguntaremos, ¿tienes la impresión de que el sistema hace que te ayude o no? Sí, pero es que después es bastante complicado eso, decir, muchas veces no pasa que lo que la gente piensa se corresponde a lo que realmente pasa. Y entonces tampoco tenemos tampoco teníamos una idea, vale, si les preguntamos eso, que es como más tiempo, que es que tienen que contestar cómo lo vamos a usar, no lo teníamos muy claro.
Lo que pasa es que a veces la confianza del usuario es importante para que use.
Sí, eso sí. Sí, en la práctica sí.
Más allá.
Sí. Esto era más de proof of concept, de decir, que es un paradigma para que, aunque no saben cómo funciona el sistema, que consigan mejorar el performance sin tener que saber cómo funciona.
¿Y habéis valorado la posibilidad de ser otra pregunta? Porque claro, tú aquí das una lista de opciones y el usuario elige y se acabó, pero no hay interacción, no hay ningún tipo de explicabilidad.
No.
¿Habéis
no lo hicimos ahora, pero sí, eso se podría también, pero eso sería también en lo de decir, más de decir que a lo mejor tengan más confianza en el sistema en sí, pero un poco la motivación era en plan que esta explicabilidad que no la tengan que entender para poder usar el sistema.
Lo que pasa es que ahí podría añadir confianza en el uso del sistema, pero también teóricamente mejorar la performance.
Eso es lo que pasa, que hay muchos estudios que es para esto de Human AI Collaboration, que la explicabilidad es bastante difícil para la persona usarla para mejorar performance, que era un poco como la motivación de esto.
Claro, que estamos hablando ahora y vais reduciendo el conjunto de etiquetas para los usuarios, ¿no? Pero, ¿qué me refiero a eso de que los usuarios
es que eso es otra cosa que también decíamos, que aquí en todo lo que, bueno, lo de los bandits y tal, del alfa, si lo tienes todo el rato funcionando, si el usuario cambia, pues cambiarías de alfa, pero no es tan fácil como eso, pero como que asumimos que no es que con esto le vamos a cambiar el comportamiento de la persona usándolo. Pero sí que es cierto que puede haber escenarios en que empiezan a usar esto y entonces su comportamiento cambia, e incluso lo que es optimal alfa también cambia. Pero todo eso en plan puedes intentar hacer algo así, pero el problema es que para después si quieres tener un experimento que sea con humanos, es muy complicado. Porque tienes que tener algo que aprendan suficientemente rápido como para... ¿Sabes? Estos experimentos, por ejemplo, es con una plataforma que se llama Prolific, que es online y tal, pero lo que dices tú requeriría que el usuario esté o volviendo, está incluso poco claro o cuánto tiempo tendría que estar para aprender, dependería de la tarea y tal. Eso es interesante, pero es muy complicado hacer algo. Puedes tener un modelo teórico y demostrar, en ese modelo teórico sí, adaptarías y no sé qué, pero hacer algo que sea que después que tú tienes experimentos con humanos en una tarea simple o algo así, es bastante complicado de que testes realmente si están cambiando. Sí, tenemos otro paper, ¿no? Que es basándote en esto, de decir en algo que se llama contrafactual harm, ¿no? Que hay en algunos escenarios donde no te interesa solo decir que tú aumentas el performance en expectation, pero una cosa que querrías es que cuando introduces una cosa de machine learning, puede ser que tú lo que quieres es que nunca pase que el decision maker, que la persona real, no hubiese cometido un fallo y por usar el sistema cometió el fallo, ¿no? Y entonces eso es lo que se llama harm. Y entonces como que modificamos esto y lo de los bandits para asegurarnos de que no es solo que en media mejore, pero que esté seguro de que haya muy pocos casos en los que pase que digamos que la persona no hubiese cometido un fallo, pero comete el fallo debido al sistema. Y entonces tenemos como otra metodología que es parecida a conformal prediction, pero no es conformal prediction, para intentar evitar eso. Porque dirías, esos casos sí que podrías decir que se atribuye el fallo al algoritmo. ¿no? Porque si la persona sola no hubiese cometido el fallo. Quieres prevenir eso. Que se relaciona un poco con esto de, en otro dominio, ¿no? De decir, si tienes una medicina que, ¿sabes?, en media mejora la salud de las personas, pero mata a unos cuantos, no consigues que te aprueben esa medicina. Con respecto a otra que mejora menos, pero no mata a nadie. Normalmente los clinical trials tienen lo de safety y tal, que antes de ver la efectividad, pues esto sería un poco lo mismo, ¿no? Que antes de decir que mejoras el comportamiento, vamos, la predicción en media, quieres estar seguro de que para individual data points que no haces que cometan fallos que no hubiesen cometido.
Y una curiosidad, ¿usáis una plataforma para hacer todo esto? ¿Incentiváis la participación? ¿Pagáis?
Vamos, para darte un... Y para el hecho de que, por ejemplo, en este experimento hicimos con estas dos cosas, dos settings diferentes, y queríamos decir que teníamos data para todos los valores de alfa, y entonces esto fue como 10.000 euros, solo para lo que es el Human Subject Study, con lo cual es, digo, porque también podrías decir, no, haces todo como solo le enseñas el valor de alfa que predices que será el mejor o algo así, sin los humanos. Pero entonces la gente te podría decir, no, pero esto en realidad, como sabes, que por eso lo hicimos un poco brute force, en el sentido de que tenemos datos para todos los valores de alfa que puedes elegir. Pero es una cosa que no es que... Y eso es con un dominio, porque dices, no, es que esto, ¿sabes? Tendrías que tener una colaboración con, por ejemplo, una cosa médica y decir, o con profesionales médicos que tengas algo así, ¿no? Pero entonces, pagar a 3.000 médicos a hacer esto no costaría 10.000 euros, pero costaría algo que no es razonable, ¿no? Entonces, ahí es más de si es una colaboración con un hospital o algo así, pero entonces no puedes tener a 3.000 médicos, tendrás a 30 o algo así, que también sería útil. Y de hecho hay un paper de Google DeepMind, que es bastante reciente, que hicieron también, allí le llaman differential diagnosis, pero es lo mismo, que es que le dan a médicos sets. Y tienen también experimentos con médicos, pero tienen como, no sé, 30 médicos o algo así, ¿no? Y es también, bueno, tienen más dinero del que tenemos nosotros para pagar a esa gente.
¿Más preguntas? Oye, pues Manuel, interesantísimo. La verdad es que es
Gracias.
un ámbito no solo muy atractivo desde el punto de vista de investigación, sino muy útil.
Esperemos.
Muy útil para nosotros, las personas. Muy bien, pues gracias.
Gracias.